Hello there. Let's see. Who do we have on the line? This is Chris Fregley. Thanks for joining. Waiting for one other panelist to come online here. My buddy Brent does not look like he's on yet. So, okay, this is, what is this? The August monthly PipelineAI online meetup here, online update, community update. So I guess just as a reminder, if you guys have questions, please type in the chat window. Let me make sure, I think you guys have access to it. Hello, please enter all questions here. If you would like to speak, of course, you can do this raise your hand thingy with the software, and I can get you in. The plan for today is to just kind of give some updates. We are recording this, so this will be posted. Let me share my screen here. And we're going to discuss a few of the latest things, a couple big things we've done since the last community update was we got distributed TensorFlow working, and it's pretty clean. It's from the PipelineAI CLI for right now, which I'll show you guys here in a sec. And what else have we been working on? Let me share my screen. Screen share. All right, so you guys should be able to see. Yeah, so the big thing, we have a customer, a pretty large customer that has very large amount of images that they need to classify, and they have a ton of labeled data, so we're trying to wrangle all that in. So a couple big things we've been working on are faster ways to get data into the pipeline to take advantage of all the GPUs and to keep the GPUs hot, that kind of thing. This is specifically TensorFlow. The other here, actually, let me shoot my buddy a quick email here. 1 second, because I think calendar invite got messed up somehow. I'll make sure he has the info he needs. If there's anything in particular that you're looking for from today's call, it looks like, yeah, there's some familiar faces here. I know you guys are working with Pipeline. Also, I should mention we've been rearranging things on the open source side. At one point, we had split out source ML into its own. So yeah, here, I'll explain this in a second. Let me get this email out. Okay. Oh, yeah, my computer had to restart, looks like, but we're all good here. We're going to cap this at exactly 1 hour, so get your questions in early. Let's see, what's his name, Brent. Sorry about this. Still getting used to this software here. All right. Still check my email, see if he said anything. It doesn't look like it. I think he'll be. Okay. We'll wait for him to come on. Not a big deal. I've got enough material to cover if he can't join for whatever reason. Yeah, he accepted the update. So, and I chatted with him this morning a little bit. Okay. So let me share again. Is this out? All right. So let me just kind of cover a couple of quick things here that we changed. So there used to be this repo source.ml off of Flux Capacitor, and I think it should be gone now. Yeah, I have it renamed sourceml.deprecated. So the thinking here, just to step back, the main repo that we work out of is this Flux Capacitor, which is the old name for PipelineAI, but it's kind of fun, so I keep it. And we have pipeline repo, and this is everything. So this is mostly training type of stuff, so there's Jupyter, there's like Kibana, and there's like Elasticsearch, HDFS support, Spark. So I actually renamed a bunch of these. These used to have the .ml extension. That's no longer the case. It was getting kind of annoying having it everywhere. Also, so there's a lot of training things in here. We've been adding these Python libraries. So, and these actually end up over on PyPy. So if I log out here, this would be what you guys see. So it'll be like pipeline. Actually, the starting point would be pipeline-AI-CLI. And that's up to version 52 right here. All of these instructions, by the way, if you start with PipelineAI, if you're new to this, start with PipelineAI here. And you can get to all of these things here off the home page. So there's the APIs section down here off PipelineAI. You click that. And there's instructions on how to install. You need Python 3. If you're going to do anything of the advanced stuff, you need Docker. I prefer Conda because you can change the Python versions and all kinds of good stuff. Let's see. Yeah, and so the other big thing, so there's the Pipeline AI CLI in PyPy. Also, there's going to be pipeline-loggers, and I'm going to show some of this stuff here in a bit. There's pipeline monitors. So the loggers is what you think it is. It's a Python library for logging. It's just reusing the existing Python stuff, but we also added Kafka logging over the past week. Because again, there's a particular customer. Actually, there's like multiple customers now that once they realized they could log to Kafka instead of logging, to disk locally within Docker and then, slurping it in and syncing to S3 or whatnot. They're actually just writing all the logs directly to Kafka. And then from there, then they can process the logs, consume the logs on their own time schedule. So pipeline monitors is a way to wrap your code and put timings around it. So this has code in there specifically. Right now, we support Prometheus, and we serve it up with Grafana, with those dashboards, but also pipeline monitors. I believe there's a pull request somewhere to support Datadog as well, and various other ones. But the main support right now is Prometheus and then Grafana. So I'm going to walk through some of that. There is another. So all of this is in this lib directory here. It's all open source. There was a suggestion by one of our community users to bundle all of these into just pipeline runtime. And so that's what we do here. This is essentially what you would depend on, and then you would slurp in all of these other dependencies. And so all you have to do is just make sure that your project depends on this runtime. And I'm going to explain what this library is here in a sec. But pipeline runtimes. So if we click on this, this will tell you the dependencies, so the different versions of loggers. Pipeline runtime, this is specifically around serving models. So that's a big part of what we've been working on the last month specifically. And let's see. yeah, so that's why you see Tornado in here. I believe we're actually moving to a different runtime. There's a pull request on a different repo that we have, an internal repo by one of our customers that we're planning to use instead of Tornado. And it's got better schema support and things like that for JSON and for structured data like Avro. And so yeah, if you depend on this runtimes, I think the version right now is 0.10, and it depends on these versions. There's actually a newer version coming out. Version 11 will be coming out that bumps up these versions to the latest. So we've been doing some testing there. So yeah, just to recap here real quick, all of this documentation here is generated in this docs. The CLI itself that I had mentioned is actually right here. So CLI is a big honkin' file here. This is where we put the distributed TensorFlow stuff in for right now. We added the Jinja templating library, so we can now do all kinds of crazy stuff. So here, this is the example here, clustered YAML, and this is where we can, with one command, we can say how many workers we want, how many parameters, the size of the worker memory. We have to beef this up a little bit and add, we have to add GPU support as well too. So we can say the number of GPU workers and the number of GPUs per worker, that kind of thing. So, but just know that you'll be seeing, so the way that this works from the pipeline command line is we would first generate the YAML that's used for Kubernetes, and then we would deploy it. So this will get rolled into one step, but for right now, it's a two-step process. You actually generate the YAML that has all of the Kubernetes service and deploy and the pod spec, and then you point it to your code, to your model training, and it will spin up all of the workers that you specify and spread the load around to the different physical nodes and that kind of thing. So that was a big update, pipeline CLI stuff here. What else we got? Probably the single largest set of changes since we last spoke would be in this predict. So pretty much everything here is all training based. There's metrics, dashboards, things like that. But this is where all of the most recent research has been going into. So you see we've updated to the latest TensorFlow 1.3, just got released a couple days ago. One thing you probably, if you are staying on the latest TensorFlow, you've noticed TensorBoard is now its own separate project. So this is a little bit tricky because if you were expecting it to be there with just pip install TensorFlow, you'll start to see errors that TensorBoard can't be found and things like that. So there's actually a separate install, and I think it's under github.com/TensorFlow/TensorBoard is now its own pip install and that kind of thing as well. So here's instructions how to install it. If you want to build it from, if you're crazy and want to build it from source, you would do it that way. Where's the pip? Yeah. So just follow these instructions. I think there's a separate README for the install, something like that. But we've updated all of the Docker images that we use for pretty much everything, the training and the prediction. All of the base Docker images go here. So for example, we've got the CUDA 8 1604. So this is CUDA 8 CUDNN 6, and all on Ubuntu 1604. So we're actually just extending the NVIDIA one, and this has CUDNN in it. As some of you who have been playing with GPUs probably know that CUDNN is typically somewhat difficult to install because it's not part of core CUDA. And so it's not free. You have to actually sign up. Well, it's free, but you have to sign up and you have to accept the license and all that. So the NVIDIA folks were kind enough to pre-package all this into one So we just extend it and set up Python 3. And at some point later, we actually get like miniconda set up. But these are just the base bare bones images here. Also, so TensorFlow base image. The latest one here is the 16D39. So these are the actual Git hash. This is Git hash for TensorFlow, and this is the Git commit hash for TensorFlow serving. So you'll see that like we actually have just TensorFlow, then or no, I think yeah, you can kind of click into these, but we have GPU versions and CPU versions. I think this is everything. This is building everything from source. This is turning on all of the optimizations, the dash full. This is like everything turned on, all the things that we use in the workshop, the PipelineAI workshop that we do periodically. And then this is just TensorFlow serving, built from scratch. Now, actually, one thing we should mention is TensorFlow serving now is its own install. So TensorFlow, I believe it's an apt-get. Yeah, so we're starting to see this more and more. Yeah, so you could do this now. You could do sudo apt-get, make sure you do the update, and then install TensorFlow-model-server. And I believe, yeah, there's some warnings here that this is expecting all of the like AVX support and all of the like vectorization, or like libraries installed for the Intel, for the newer Intel chips. If you don't have that type of hardware, which is actually relatively common within Amazon, if you use some of the older like R3 instances and things like that, they may or may not have AVX turned on. This is something I've seen less of with Google, mainly because they kind of started later. But I definitely see it about half the time if I'm not careful about which physical hardware instance that I use. Also, jumping back real quick to CUDA stuff, for those of you doing CUDA stuff, just know that when you're trying to get GPU things working, this is very dependent on, I'm going to bounce over to the wiki here. So this is still within Pipeline repo. Just going to bounce to the wiki. I'm sitting in a hotel here on the East Coast, so my connection's a bit slow. But here's updated instructions for Pipeline plus AWS for GPU, for CPU. And let's see, either the ones that you probably want to take a look at are set up AWS and GPU and set up Google and GPU. I just updated these instructions. Just know that with every new kernel release that like Amazon or Google put out, you could potentially be breaking your CUDA, or like the NVIDIA drivers and all that stuff. So these are full instructions on which type of instance. Just know you probably want to pin yourself to if you just select Ubuntu like this, sort of generically. Yes, Amazon has its own like distribution of Ubuntu with security patches and optimizations for the Zen hypervisor and all that kind of stuff that works for their environment. So just know that like occasionally they do update it for security reasons, and if that happens, sometimes your CUDA drivers won't work. So this is why if you are doing GPU stuff and you're like Googling around and you see someone's instructions to set up NVIDIA, you know, and Docker and the CUDA libraries and the CUDA drivers, it may work for them, but it might not work for the particular cloud instance that you are on at that moment in time. And this has burned me more than once. There's a way, so I've updated the latest. I think everything works as of about a week ago. These should all work, and we'll get you going if you do want to set up. And this gets Docker going. And this actually, you can pull down the full workshop that we do, I think, about once a month on a Saturday. I believe there's one coming up here. Maybe next weekend, something like that. But yeah, this is using the NVIDIA -Docker. So here's the actual Docker image that we build periodically. So it has TensorFlow, Spark, and working with GPUs, and it's opening all these ports. And and then this way you can verify it. And yeah, you could actually do some cool GPU stuff for, you know, just a few dollars, and then you can kill the instance when you're done. So this is the AWS instructions. Here's the Google instructions. These have been updated as well. One thing I did, the most recent workshop I did, I had a problem where it was that exact issue I mentioned where the kernel got updated. And I use the command line when I'm spinning up these GPU instances, because I'm typically spinning up about 300 for these larger workshops, distributed workshops. Just know that there is a way to actually pin, not just Ubuntu 16.04, but you can actually say this particular date. And this has a fixed, this has a fixed Linux kernel. You could choose, if you want to update it, but the whole point here is to not update it, to go back to the last known good that was working with these drivers. Now, I actually think that you can use the very latest now because of these updated instructions, but I still pin it. And I'll show you guys the command line for that. Down here, so this is using gcloud. Here's where you specify the minimum CPU. Now, this is interesting. This was something new that they added a few months ago. This is Google. I don't know about Amazon if this is possible. I think the instance types, they don't guarantee the like the actual Intel CPU hardware. But here you can tell Google that at minimum I need Broadwell, and the Broadwell chipset has the AVX support for CPU vectorization for the instructions to like operate on vectors instead of single elements. So very important from a throughput standpoint, performance standpoint. Here's where you actually pin it to a particular image. Here's where you tell it the type of GPU. There's only one type right now. At some point, this will be Google-TPU. For Google specifically. So this is the exact setup that I use when I spin up instances for the workshop. Here's that same NVIDIA Docker thing. So it's just scripted here instead of doing it manually. Okay. Let's see. Let me check the chat here. Okay. And looking for. Just check my phone, see if Brent is calling in. Okay. No. Okay, so yeah, those are a couple updates there. Again, this is all open source stuff, so everything's there. If you guys have questions, email help@pipeline.io, and we will triage them as they come in. So as part of this API off of the main pipeline site, we can scroll down, and this was something I showed on the last call. I think I've updated the instructions a little bit. So once you install pipeline-AI-CLI, then you could just run pipeline. It's just a Python CLI, and this is a way to actually build the Docker image, build your model into, like burn your model into the Docker image after it's been trained. And then you would, instead of shipping the model, and like handing it over the wall, you would actually hand over the wall this Docker image that has the particular runtime for the type of model that you're deploying. So I'm trying to go through those steps here because and then you can also keep time log. So the way to think about this is you would train the model however you want to train it. You can use the distributed TensorFlow stuff. You can use Scikit on your local laptop. You can do whatever. Once you actually package the model into a Docker image, you can actually test it locally, and you can hit a REST endpoint. We've been adding Kafka support as well too. That's where some of the Kafka logging stuff came about from pipeline-loggers. So a lot of that stuff's in there. And yeah, these are just screenshots. We use this open source project called Guild AI. I can pull that up here if you want to check it out. It's a buddy of mine out of Chicago, my hometown. He actually, if I could, so he's got a really cool website. You can check that out later, but I want to show you GitHub. So we strong-armed him into rewriting it. It was formerly written in Erlang and Bash scripts and all kinds of fun stuff. He's a whiz at like that kind of stuff. But we convinced him to replace Erlang just to make this more usable and acceptable. So think of Guild AI as a packaging type thing for your models. So it has this guild.yaml file that describes your model. So I think I can actually show one here. The Python rewrite is still in progress. I think it's mostly at feature parity with the old like Erlang version, but there might still be a few things missing. Where did I have? I missed. So yeah, for the Erlang version, it was this INI file that described it. And think of this as a way to describe your model. And the Guild actually supports more on the training side than on the serving side. They do have a serving component, but I've been working with my buddy too. And I think probably the next call next month, I'm going to pull him in. I was trying to get him in last night. I was texting him, but he's got stuff going on today. So, but yeah, this is where you would actually define your training hook and your preparation. So and this way you can pass parameters into your custom training.py file. You can pass in learning rates. I've been working with him on getting support in here where you can specify ranges for like a grid search kind of thing. So you could do hyperparameter tuning, and this combined with the new distributed TensorFlow stuff that I've been working on personally, we're going to try to merge these into one thing within this pipeline repo, and then you could actually run multiple experiments with different learning rates, different hyperparameters, different batch sizes, and that would all be coordinated. So this is actually the old Guild file. That's one I'm actually more familiar with, but here's the newer YAML version of it. So, and there's these different profiles. So you could have a profile, for example, called intro that has a set of parameters. You can have a profile called expert that has another set of parameters, just kind of like one example. But yeah, you can imagine the other things here. So like, yeah, so once again, this is more on the training side of things. And then once the model's trained, then you would actually pull it in to PipelineAI's predict stuff. So let me bounce back to the predict stuff and just keep going down that path. So inside predict, this replaces all of the other. There were about 3 or 4 projects formerly that handled predictions, and I had broken them up into separate separate subdirectories and separate Docker images because they were logically separate in terms of their like runtime capabilities. So things like if it was a Python model, if it was a like JVM model, right, like different like runtimes would start up different processes, things like that. So instead, I had moved all these into one runtime. It was just getting a little bit difficult to keep managing those, and now there's one big gigantic Docker file that looks. And so right now, keep in mind that you would be training offline, or right, like you'd be training with Guild or with some other cluster. And then this is where you would run the pipeline model-build. And it's essentially, it's going to run this Docker file, which slurps in your model. So one of the parameters that you pass in here is model path. So if you're not familiar, Docker lets you pass in like arguments that are build time arguments, not runtime arguments. So these get used for the scope here. So model path, okay, model path, what was I doing here with this? Copy model path, brings it in there. Yeah, oh, okay. So inside of this Docker image, when it's done building, there's only going to be one root/model directory, and that is going to contain whichever model that you pointed to. So let me show you here. So model-build, this is what actually creates the model, or that new Docker image, right? And you would want to tag it with something more than just master. I don't use the default latest thing because defaults are evil. So yeah, try to always tag it, at least put the date in there, version number, you can choose whatever you want. I purposely call it tag so it's not version, so you're not taking numbers. You can use git hashes, you can use whatever you want. And the output of this will be a Docker image that has this, and this in the name. You could also specify, like there's a couple other parameters you can specify, like model chip, and this could be CPU, GPU, depending on what you're actually building. So you can differentiate too, so you could have a CPU version and a GPU version of the same Docker image, and it'll load some of the libraries differently and yeah. So this one single Docker file handles all this. A couple people have asked for if the model isn't living locally because it's it was built by somebody else. Maybe there's an HTTP endpoint. We've got the start of some of that here. Things were getting a little bit wonky this way. So instead of, and yeah, other people asked about S3. We've got a couple customers who have models that are, half a gig, 500 megabytes. They don't fit into GitHub. You can't very easily do a git pull. They've tried the GitHub LFS, the large file system. That thing has not been stable. From what I hear, I haven't used it too much. When my models get big, I just put them into S3. We've since commented this out. It's still here for people to review, but we don't want to make it the mainstream because it's just going to be too much to support. There's just too many. So the thinking is, whatever you have to do to get this model to wherever you're running this pipeline model dash build, that's up to you. So for example, if you're running this within a Jenkins job, you would have to, as part of the Jenkins pipeline, the build pipeline, you would have to actually pull down that model from S3 or from wherever it exists, and put it locally inside of the Jenkins workspace. Okay, and then there's just a bunch of if statements here if it's TensorFlow. So even though logically there's only 3 or 4 different runtimes, there's TensorFlow serving is one runtime. You can also run TensorFlow just with Python by just calling session.run, for example. But I still wanted to keep them all separate, right? And yes, obviously scikit is just, it's the same as Python, except it's just using different libraries. I still want to keep them separate in case we do at some point start to tweak some of the implementation specific to Keras or specific to scikit. So for now, we're, every sort of logical type of model, you can just do plain old Python. You can also just do plain old Java also, and that will use the JVM runtime beneath the covers. You don't have to think about that. You just supply pipeline number, the pipeline underscore predict method. So here's the pip install for the new TensorBoard stuff, by the way. Also, here's a Kafka Streams library. We're starting to do quite a bit with Kafka Streams, and this is for some of the more advanced use cases that we've been handling from some of our customers, which I will go into here in a sec when I talk about some of the newer things that we've been working on. All right, so just know that there's one big gigantic Docker file now, and it will dynamically. So based on the model type that's passed in here, so this one would be TensorFlow, it will figure out which things it needs to pull in and build. And we still haven't gotten around to actually optimizing the size of the Docker images. There's definitely quite a bit of room for minimization of these things. They're starting to come in about 3 gig, 4 gig, which is definitely a concern. Hasn't been too big of a concern just yet. Some of our main people are these larger customers that are just totally fine, with these larger Docker images. It's just oh yeah, one thing to keep in mind too is that this is the open source version here, and this Docker file also installs let's see, what does it install? It installs Prometheus, it installs Grafana. So the assumption here is this is a single node that is running, it's running the metrics, it's doing the logging, it's doing all the roll-ups, and serving up dashboards, things like that. So, and it's doing all this at the same time that it's serving up the model through, REST endpoint and through a Kafka stream. So not the distributed way to do it, not the proper way to do it, but this is the single version. This is the best way we can get things out here, and people to start to play with this and like give us feedback, and not be burdened with setting up a Kubernetes cluster, or dealing even with like Minikube. Has some quirks, and it just kind of broadens the surface area, the support surface area. So we decided it was best to just jam everything into one single Docker image for the open source version. Okay, and let me back up here, point out some other things here. We clean. Oh, so here's some templates. This again works in conjunction with the PipelineAI CLI that is over here on the right that you can install. And these are essentially Kubernetes templates. Let's see, so if you're familiar with Kubernetes, there's deployments and there's replica sets. And let's see what else. Yeah, all the ports that need to be open and that kind of stuff. So also there's a service. This is the load balancer to make this endpoint public. This way you can, right, so again, this is one single Docker image that will get deployed to a Kubernetes cluster if you do want to use Kubernetes. So, but it's not truly distributed, right? This is one single Docker image that gets deployed, and then all these ports get open. And but you still have the satisfaction that you're using Kubernetes. But if you do want the distributed version, you have to come talk to us, because that one's a bit more complex, quite a bit more complex. Okay, what else here? Configuration. I think everything's. Oh, so we've got as part of this Docker image, we've installed Nginx. So that's actually the front door for every call that comes in. And if we look at the configuration here, so the main port is port 6969. This is just so that if you do have something running on port 80 or port 8080 or whatever the common ones, we just chose kind of an oddball port. But yeah, anything coming into here will then get routed. If it's /Prometheus, it'll go internally to port 9090. If it's Python, things like that. All these Python ones, including TensorFlow right now, actually go to port 9876, and that's where the actual Python Tornado server is listening, and then pulls in the model and then makes predictions off that. If it's anything Spark or PMML or Java, XGBoost, even R, it's using the Java backend, which is listening on port 9040. All right, so that's kind of how that goes. The reason I point out Nginx is this is how we are starting in the open source version. This is how we're starting to do the traffic routing and traffic splitting. Meaning when you push out a new version of your model, if you want 5% of traffic to start going to the new version, right, like the Canary version, you can actually do that with Nginx. So it's not the most dynamic way to do it, because when you do make the changes, you have to reload the configuration. But this is much easier than the distributed full version of PipelineAI, which is using Kubernetes and this routing tool called Istio, I-S-T-I-O, that we talked about on the last call with one of the creators of that project. So if you're interested more in some of the advanced routing stuff, again, talk to us or go look up that particular talk. But the simple way to do it is to just put percentage. Can't remember the exact syntax, but for example, you could have /Python/Canary or /scikit/Canary, and that would have 5% also, and then you would have scikit/current. So there'd be current, and then there'd be Canary, and then this is what you're comparing. And so yeah, traffic would get routed that way. So for demo purposes, this is just fine because we're not really dynamically. But so the advanced version that's using Istio, that's all right. That's where you are going to start seeing the multi-arm bandits and the dynamic shifting of traffic. This is probably, again, a much more difficult problem and has a lot of high availability concerns and fallbacks, and yeah, definitely like a much more difficult problem that way. All right, so that's Nginx. I had mentioned some of the Kafka stuff. Let me show you guys an example model. Yeah, one of the models I tend to experiment with pretty heavily is this TensorFlow MNIST one, because this has a lot of the complexity of both TensorFlow serving runtime, which is a separate model server, C++ based model server, much faster than if you just call the TensorFlow Python session.run. But one thing I do want to highlight, so here's the pipeline_predict. Yes, so this would be like if you were creating a custom model. I have examples here that's within the predict, but within here is models, and then I just have all the different versions that or types that we currently support. I'm missing R, I think, in here, and maybe one other one, but the one that I tend to play with quite a bit, just because of complexity, is this TensorFlow MNIST. And this one, so let's take a look. Yeah, so so here's what, and so this is just one convention. You don't have to actually follow this convention, but there's kind of a base models directory, then it's broken down by type, and then it's broken down by the model name. So if we go back here, you'll see there's actually two different models. There's just linear regression. This is what I use for the workshop. And then this is the more complex MNIST. Both of these will have these pipeline underscore files. So the pipeline runtime actually uses or looks for pipeline underscore and is expecting certain things. So let me actually back up here and go to MNIST. You'll see pipeline underscore predict. Oh, and then just real quick too, in terms of when we're loading, so like keep in mind that when you run this pipeline model dash build, the output of this is a static Docker image that is not meant to change. So it's got the immutable property. And we had gone this route because we want to force, right, like the immutable architecture and not, have to like deal with these model servers getting updated dynamically. It's much easier. I saw this from places like Netflix and Databricks and IBM, that much easier to just tear down the old cluster and spin up a new one, or have them both running side by side, rather than trying to upload the model to each model server and keep your fingers crossed that it's actually being updated. So the output of this is a static Docker image that has your model burned into it. So, here, for example, is /model/TensorFlow/MNIST, models TensorFlow MNIST. And this actually, one of the steps, the very first step is to run this conda. So, we're assuming conda. This seems to be universal. Everyone that we've talked to, all the data science teams, across a couple dozen customers, they all say this is totally fine. So people like conda because you can actually specify a different Python version. Some of you might know that Spark and Python 3.6 don't go together very well. So if you do have problems, you'll have to back up to Python 3.5. It's kind of a side note there. But yeah, so here you can actually, when you run pipeline model dash build, if it doesn't find this, the build will fail. And so this is important here because this defines the version of Python. This defines all the dependencies. So if you want to pin to TensorFlow 121 for some reason, or the particular pipeline dash runtimes I was pointing out before that gives you the loggers, the monitors, you would do that here. So that's kind of the entry point. We had a couple use cases pop up where we finally decided to just put this in. It's a generic shell script, bash script that you can specify. And, here yeah, I'm just explicitly installing a different version of pipeline loggers just to show that you can do that. But this is where you would do things if you, the one use case we had was the model prediction actually needed to join data or load in reference data upon the model server starting up from a SQL server. So we actually had to do like a pip install and then get the ODBC driver in. So that was one use case. Was like, all right, yeah, we'll give a generic shell script you can run. So, right, but again, this all runs when you are building the model, like Docker image. So not actually at runtime. And so again, this was a intentional decision. This also comes from seeing Netflix, where we had a case where we did have dependencies when the model servers would start up. They would have to connect to a configuration server and to S3, and they would have to pull data from places. And we decided it was much, much easier to burn all that stuff in. In that case, it was into the Amazon AMIs. Here, it's into these Docker images. So the more that you can do at build time and the less dependencies you have, the much better off you'll be. The problem there is when you actually do need to scale up quickly or to shift traffic because of a region outage, if you do depend on S3 or on EBS or on, you know, some sort of, if you depend on Cassandra, if those dependencies are down because of this, you know, huge outage or right, like whatever's going on with your cloud provider or your like data center, if there's network partitions happening, you physically cannot ship the traffic because you are not able to spin up instances because of these broken dependencies. So right now there are 0 dependencies the way that this is architected. So these model servers pop up completely independent of any other runtime. They're completely self-contained. All of the Python libraries have been retrieved. Yeah, everything specified in this conda environment.yaml. All of that stuff has already been retrieved. If you, the pipeline install.sh has already run, so this would have installed the ODBC driver already, so none of this has to happen upon starting up. So let's take a quick look into pipeline_predict. And I just want to highlight some things here. So here's our pipeline loggers. Here's pipeline monitors. Just ignore pipeline models for right now. That's specific to the way that we're handling TensorFlow serving. But yeah, so let's just, and then also there's this loggers Kafka. So we're setting up a logger here. This is just standard Python stuff. We just added a Kafka handler that you know, so here the configuration is static. It's because this is all running within one Docker image, there is localhost, and you give it the name of the topic. And so I'll get to this here in a second, why this is called prediction inputs, but I'll show you a pretty clever use of Kafka and some of the features that this enables us here, specific to model serving and some of the metrics and some of the insight that we're providing with PipelineAI. Okay, so we also, as part of pipeline loggers, we have this decorator called log. So, you know, Python decorators, you can essentially, if you think of them, like annotations within like Java or Scala, you can sort of, you can decorate your Python methods, and they act as sort of interceptors as well too. So right when the method's called, it'll first call the decorator, it'll pass it all the arguments. You can do fancy things in there like log timings, you know, so if you guys remember aspect-oriented programming, this is probably the closest thing Python has to that. So sort of horizontal cutting concerns and code you can jam into these decorators. So they're pretty cool from that standpoint. So we got that, and then we have monitor also. So monitor is going to come in handy here. I'll show, but let's first show a log. So we've got this kind of generic set of labels that you know, for now, it's just the model type and just the model name. You could also add if it's CPU, if it's, you know, GPU, you can have whatever you want here. But for this purpose, it was good enough just to know which type of model and what the name is. This way we can differentiate We may want to add tag in here as well too. Actually, we probably definitely should add the tag in here. That way you can differentiate different versions. But what's happening here is we're passing in those labels, so they'll automatically get appended to each log line. We also then pass it a logger, and remember that the logger is not only writing to the console, but it's also writing to Kafka, and it's going to look for this particular. This would be a list of brokers, and for like failover purposes, there'd be rather more than one there. And then here's the topic. So you wrap this method, and what this particular decorator does is like this predict method is totally generic. This is some of the work that we're starting to do around schemas. So we're putting in better typing, stronger typing for JSON and things like that, so we can actually have some sense of the structured data and can enforce it at like this level as well too. So we could actually fail and say this request is not properly formatted, like relative to the schema that was provided at build time. So please reformat. And then also, so this is Python 3.6, so we can set types here, which is very nice. These types aren't really enforced. It's more for readability purposes, but you can run something, I think it's called MyPy or something like that. It's one of those Python lint like processes that can scan your code and like figure out the types and then tell you if there's anything bad going on there. So that's kind of nice to have as part of your build. Makes these methods a little bit more explicit, and you can actually have a chance of understanding what they're doing. So this log thing just takes whatever inputs have been passed in and just writes them out. Now, you can actually pass in a custom formatter. So, so because this is defined at the method level, this is going to take the request and it's going to log the response. And what we're doing here is we're actually logging the raw features that are being passed into this prediction. We're transforming the raw. So in this case, if it's a like web request, this would be JSON. There's this method underscore transform requests that takes the JSON, converts it into NumPy, passes it into the model, which in this case is a TensorFlow model, which can handle NumPy arrays. It'll just convert them to tensors and back. And then there's the other way, transform response. So here it's converting the raw input, which is JSON, into NumPy. Here it's taking that transformed request, passing it into the model predict, which is TensorFlow. And then it's taking the response, which is a NumPy array or tensors, and it's transforming it back to the raw response, which in this case is going to be JSON. So what we're doing is we're logging the raw inputs, we're logging the raw like predictions. So the features are the inputs that's coming off of this like web request for the prediction. Yes, also we can also do Kafka streams as well too. So this same exact code, because we have this Python's Kafka streams library that we're using, we can actually use this exact same pipeline_predict file and this predict method. And instead of passing JSON, we would be passing like an Avro record. We would have to change these transformers to handle the Avro and do some of the schema validation, things like that. But yeah, so like logically, we are able to log the raw inputs. We're able to log the raw outputs, which is predictions. We can also, here we're putting timings around each of these. So this is super important. This was one big thing that we heard over and over from customers was when their predictions start taking 500 milliseconds, 600 milliseconds, they don't even know where to start for the tuning. They, like typically because they're the ones working on the actual model itself, they're going to start tuning the model. What we found is most of the time, probably 80% of the time, it's not the actual predict method that's taking time, it's these transformers. And people do all kinds of crazy stuff in here. They use pandas CSV to NumPy, or to like pandas methods, which just take ungodly amounts of time. So there's a lot of tuning that can be done, and so this type of insight and this type of monitoring, this gets fed. So these monitor tags down here actually get fed into like Prometheus, which is then exposed as a dashboard. So you can actually see where is time actually being spent, and you have full flexibility. So you can use this as a monitor, or sorry, as a decorator, or like you can actually embed it like this. So here's a way we're using Python's context manager. So this is the exact same monitor, except it's used as a context manager. Same exact methods, but now we're actually wrapping it, instead of the whole method, we're actually just wrapping this predict call. So this way we have distinct timings for transform in, transform out, and then the actual predict. Super valuable. And so you can turn that on and off as needed. Let me get back to the logging thing real quick. The benefit of logging the inputs and logging the outputs is you can then, actually, let me pull up a cool image here that I just added. I was doing this right before the call. We've got a quick tour here that takes you through. This actually comes from our work with some of the VCs recently and some of our for the like pitch deck and that kind of stuff. So let me continue on. Yeah, so you guys can do this tour yourself. Just a basic type form thing here, defining the problem. So yeah, one of the problems here is when you do push the model into production, you suddenly don't have any insights into what's going on. There's also no fallbacks. If this new like predict method or these new transformers start taking 1,000 milliseconds, 2,000 milliseconds, there's no fallbacks in place. So these are some of the problems Pipeline is solving. This is around multi-arm bandit tests versus just traditional static A/B tests. Here's some stuff about hyperparameter tuning, taking into account the prediction time. So like imagine, so this is a slightly different use, or this is a different use case, but still using some of these online metrics. If you do suddenly start to do different learning rates and different hyperparameter tuning, so picture you have a decision tree and the current version might have 15 levels deep, and the new version of the model is 200 levels deep. So maybe at the actual training time, when you're validating the model offline on batch data, this is fine because you're just looking at the accuracy. But now when you push it into production and it's running alongside the existing model, this new model on the prediction side now takes 500 milliseconds, 1,000 milliseconds, whereas the old one that was only 15 layers deep took 5 milliseconds. So being able to incorporate time prediction side on live data, on streaming data, is super powerful versus just looking at the offline metrics like things like accuracy. So let's see. Yeah, this is really hard. I have to work on some of these things here. Yep. All right, community. Let me show you feature, and then I think it's 1 o'clock here, so we have to go. But let me show you this one image. Is really cool. I really like it here. This one. It's too small. This will sum up, and then we will wrap it up here. But let's see. Oops. Python tax. Here. Looks like I might have messed it up here with this feedback thing, but yeah. So let me show you guys what's going on. Just ignore the feedback thing. Up here is sort of the batch these batch metrics, things that are, so this is batch offline. This is just looking at accuracy. So the current model has these particular metrics, took this long with this learning rate, and now we're starting to experiment. So now we have this new model B, this new model C. One thing we can look at, because we're logging the inputs and we're logging the outputs. So now, like, imagine a dashboard, and here's kind of a mock-up of it here, where current model, this is how it's predicting for, given set of inputs, that's what it looks like. And we're also, at the same time that we're predicting with model A, we've pushed out B and C into canary mode, and those are getting the same inputs. And so now we can see, for the exact same inputs, what are the predictions. And so model C looks to be pretty close. So in terms of precision, A and C, so A is our current control, B and C are the new experiments. C actually looks to be tracking pretty well with A. So that's good news. So in terms of predictive, the actual outputs, the actual prediction values themselves, and there's different ways to chart these. You could, for example, if you're charting search results, you would have the top 10. You would do something like a Jacquard similarity, where you look at the recommendations from the current model, from experiment B, experiment C, and you would have the top 10 and figure out the distance, right? Like Jacquard similarity, Jacquard distance, which is the set union, or what's it, the set, it's the intersection divided by the union of those sets, and you could actually plot that number here. So obviously, the more similar, the closer they will be to 1 based on that particular formula. So you would want, and then here, experiment B looks to be sort of way out of tolerance. So B loses in terms of the outputs. Now let's also look at the runtime, like the actual response times. So this is some of the system metrics. One thing to note here at the very bottom, I didn't do a good job highlighting this, but at the very bottom is the actual prediction time, the time spent inside of the prediction, that method. So 16 milliseconds for our current. The whole point of doing this experiment is to check out how the predictions are comparing to the current model, and then secondly, how much faster is this, or is it worth putting this model out? If it's slower, then no. But so yeah, here's a case where it's 16 milliseconds for the 90th percentile versus 7 versus 1, or if you want to look at 99.5 percentile, 28 milliseconds, 20 milliseconds, and 17. So C wins here as well. So at this point, we would actually scale out C and replace model A. And so this can all be done with just a few clicks. Let's see what else here. Yeah, and then there's one other cool thing you can do, because you are logging the inputs and the predictions. If you do have some sort of threshold set up, so let's say there's a classifier. You're trying to do hot dog, not hot dog. So here's a perfect example. This is actually a real world case here. I was at my friend's place, and we were setting up a hot dog, trying to fool the hot dog, not hot dog app from the TV show Silicon Valley, which is an actual app that uses TensorFlow. And this was a case where we are assuming that the actual confidence was about even, because in one case, the exact same hot dog, just slightly tilted, the classifier was able to recognize it. And then I think we just added like a little bit more ketchup, and suddenly the hot dog was not recognized, even though it was like the exact same. So this is a case, for example, where the confidence values that would actually get logged in the prediction. So as part of the single log line, you would have the inputs, which would be this particular hot dog image. You would have what the classifier predicted. It would likely say 51% hot dog and 49 not hot dog for the first one, and then the opposite for the second one. If there is certain predictions coming back that are sort of close to the 50-50 and not confident based on your definition of being not confident, some threshold, you can actually pipe these into its own Kafka queue, so Kafka topic. And we actually have one customer who is pulling, and when it sees those, it's actually pushing them to Slack. Now, there aren't too many right now, just based on, and they're sampling, of course, and making sure that the team's Slack channel isn't getting flooded, but they've created a separate Slack channel that is being fed the actual image and the model's prediction. And then it's up to the humans. So they've been calling it crowdsourcing. That term's a little bit scary because it sort of implies publicly crowdsourcing. That's not the case. They actually have their own team right now is just manually label, so like manually overriding these labels that the model is predicting. And then they go into a labeled sort of update queue that then gets fed back in during training time. So they're actually helping the model improve with this manual intervention. Now, this doesn't scale, of course, because these teams are small and probably more and more data is going to be coming through as they expand this particular use case throughout their app. So they've been speaking with companies like Crowdflower and places like Mechanical Turk and probably getting various quotes there. But the plumbing is all in place, and all you need is a Slack channel or some way to consume off of a Kafka topic, and you can now start to actually take live data that's coming in. So this was from my phone at my friend's house. This is previously unseen by the classifier, and it was not confidence, but now you're actually overriding it and improving the model. So people get really excited about that use case. That's a fun one. And let's see, I think last feature here. So some intelligent ensembles. This is some of the other stuff that's coming up for the next call in a month. I'll be explaining some of our work around ensembles and ways to put intelligent timeouts when you are ensembling different models, especially in a distributed scenario. We have one use case where people have a legacy, basically REST-based model server that's in a separate system maintained by somebody else. That system is not always up. So if that system is up and they can get to it and that prediction comes back in a reasonable amount of time, 20 milliseconds, 25 milliseconds, then they will incorporate that prediction into the ensemble. Right now, there's no way to set up timeouts. There's no way to, not deal with it. Like, they essentially fail the entire prediction if the dependent service is down, and obviously that's not a good thing. So just sort of adding more intelligence, coordination for these different ensembles is a pretty cool deal. All right, so that's the latest. If you guys want to put your email in there and get more information, I'm sure a lot of you already have. That's why you're on this call. But let me check the chat real quick. And my buddy Brent, we'll have to get Brent on the next one. I think he got confused because I'm having a call with him later on today. So if there's no other questions, I'm going to let you guys go. We're 10 minutes past, and I'll post this video on the YouTube, the PipelineAI YouTube, and I'll talk to you guys soon. Thank you much for calling in.